Alright, hell yeah, I just got off the comment section and someone's like, hey, you know what I mean, you should do problems out of this book. And I was like, send me a link. Actually, just send what problem you want me to do, you know what I mean? Maybe I'll have a donate button. But anyway, so we have a car that starts from rest on a half-a-kilometer long bridge. Now I'm going to read this one because it feels like it makes no sense. So we have the coefficient of friction between the tire and the road is 1.0. Show that one cannot drive through the bridge. See, this is just written like, are they talking like over the bridge? You know what I mean? But anyway, through the bridge in less than 10 seconds. But so besides just kind of the word, yeah, you just don't know what's going on. But anyway, and then I just realized this problem's online, you know, and a lot of different people solve it. So I'm not going to look at any of those. Like, I haven't looked at anything, you know what I mean? Maybe I saw just a quick glance of someone doing, you know what I mean, like this, your classic, well, we have a mass of a car, we must have some weight, we want to go this way, hopefully, but we got some friction due to a normal force, and the friction force is mu n. So that's kind of, I already knew all that stuff. But this one was just like, what are they even talking about? You know what I mean? Is this bridge like on a hill? Like, is the car even work? And then I was just like, oh, so is this one of those problems where you're just like, you know, like the it's just physically impossible? Like, so one thing that I went to is just like, well, what's the fastest car in the world? What's the fastest accelerating car? That's going to be that's the first direction I'm going to. So the foreshadow is like, well, a human can't sustain, you know, more than 6 Gs for a very, very short amount of time. You know, about 3 to 4, maybe 5, maybe 6, but definitely when you get above 6, you're kind of into that death zone. 10 is death. You can sustain 10 for a very short amount of time. But anyway, so yeah, you can go. So let's do this. So let's do this problem, and it'll help us do this problem just to feel it out. And friggin' A, let's get to it. So if we have a car at rest, this car has zero speed. We're going to do everything in meters per second, so we're going to convert all this to meters per second. Because our problem, we need to go a half a kilometer. We need to go 500 meters in 10 seconds. Cool. Oh, and so even just right there, people ask, like, well, how do you solve problems from just, like, the get-go? Well, one of the things is, like, the units are the equation. So acceleration, definitionally, is change in velocity, change in time. If you're doing any sort of kinematics, you know, just write this one down. Also write velocities, change in position, change in time. So, so let's say, and then let's just guess, you know, yeah, I really want to do that for this one before, like, actually pinning something down. So we have to go 500 meters in 10 seconds. Well, oh, so we have an average velocity. You know what I mean? So velocity average is your distance, 500 meters in 10 seconds. So we have to go 50 meters per second. So that right there is insane because, you know what I mean? If you're... See, I'm in America. This number doesn't mean anything to me, except I know that to multiply by 2, and then some change. You know, 2.25. I call it the multiply by 2 and then 25% tip. So I can even do this one in my head. I can multiply by 2. That's going to be 100. If my bill is $50, I got to give 25% tip. Don't know it, but if I give $5, that's only 10%. So I better throw in another 5 for 20. So cool, we're at about 110 miles per hour. But what's that extra 5? What's 5%? I don't know, but I know 10% is 5, so 5% is 2.5. So we're 112.5 miles per hour. This would have to be our average speed. So maybe this problem is, that was the aha moment. It's just like, what are they even talking about? Like, you should always, this is like one of those trick problems. I think it is. But maybe we'll get to it from a coefficient of friction perspective and see what that actually means. Because you actually have to grip the road with your weight. Your weight is determining how much gripping force and all that jazz. I have no idea. But if the person is just like, hey, I just want a new way to look at this problem, well, I'm giving you a fresh perspective, because this is your average velocity. So guess what? You start at 0 velocity. Your velocity is 0. And if you have an acceleration that's constant, just a continuous change in speed, to have this as your average speed of 500 meters in 10 seconds, is that what we have? Half a kilometer. 1 kilometer is 1 kilometer. That's 1,000 meters. We have half that. We have 500 meters. And we cannot drive in less than 10 seconds. Because we would have to do this, you'd have to double it. So this happens in kinematics all the time. Sure, this is my average velocity, but guess what? We're starting at 0. And we're just going to say the acceleration is constant. Now, maybe you got like a dragster wheels, they're so underinflated, the second you start to actually get going, they start to layer up. They kind of fold and flap underneath the wheel. They totally flatten out, and you get all these frictional folds, and hell yeah, you got a ton of friction that's able to take that very light roadster just with a heavy ass engine up to speed. You know what I mean? So cool. But anyway, so yeah, you got to double this. So we would have 125. Yeah, I mean 225 miles per hour. So 225 miles per hour, or just 100 meters per second. That would have to be your top speed. Now 225 miles per hour, that's doable. You know what I mean? So nothing wrong there. Alright, hell yeah. So now we got a problem. But what did I talk about? Acceleration. You know what I mean? Let's see if I actually want to know this one. We're going to do this one. Because if this car is going 0 to 60, and let's get a factor label on converting miles per hour. So we have 60 miles per hour. Let's write it like this. 60 miles per hour. I'm going to say 1 hour is 60 minutes. I'm going to say 1 minute is 60 seconds. Hell yes, now we got seconds. Hours cancel, minutes cancel, we got seconds. We got to convert miles, so we got 1 mile is 5,280 feet. Okay, 1 foot is 12 inches. Oh man, we're running out of steam. So, and then we got 1 inch is 25.4 millimeters. I like to do this, and then I go 1,000 millimeters is 1 meter. Hell yeah, so we got meters. So now, instead of, 60 is our input, and then all this jazz is what we want to multiply by. So we're going to do 1 divided by 60, divided by 60, and see that's just the inverse of 3,600. Cool. We're going to multiply by 5,280. Alright, so and then multiply by 12 times 25.4 divided by 1,000. And 60 miles, yeah, so, and then the inverse of this is that 2.237, that was that 2.25, times 2, 25% tip. Okay, so we have a conversion factor of 0.44. Oh, I didn't know this was an exact conversion. Hell yeah, because millimeters to inches is exact, I think I'm going to memorize this one. How hard could it be? 4.44704. It looks really hard to memorize. But that's going to convert miles per hour. So if I have 60 miles per hour, this output is going to give me meters per second. So this thing is going to say this is hours per mile. Now how does that work? Hours per mile, meters per second. I don't know. I guess the units on this are cancels the hours, cancel. Yeah, it's all those units. But anyway, it is the conversion for that. I'm going to store that in my calculator as X. Holy hell, we just got to get to it. Okay, so we have 60 miles per hour, and perfect. So we're going to take 60x. So this is 26.8 meters per second. So so cool. And we're doing that in 1.55 seconds. Okay, hell yeah. So definition of acceleration is change in velocity. So we have a change in velocity of 26.8 meters per second. We did that in 1.55 seconds. I've always wanted to know what the acceleration, like what would you feel like? How many G's would you be pulling in your seat? Divided by 1.55. And we only have 17.29 meters per second squared. That's a change in speed of 17 meters per second for every 1 second. Now free fall is 10 meters per second If you jump off a cliff into some water, every second you're going to be going 10 meters per second faster. That's 22 miles per hour faster. So for a 2-second free fall, which is totally doable for like a 65-foot cliff, you're going to be going 45 miles hitting the water, 45 miles an hour. Okay, so the acceleration isn't too crazy. It's just 1.7 Gs. That's all you're pulling. In this car, you're going to pull 1.7 Gs. Okay, so now, I don't know, you know what I mean? So now I think we just have to kind of go to this drawing. We've determined that it's theoretically possible. Hell yeah, you could have a car. I mean, this car is going 0 to 60 in 1.5 seconds. So let's continue that acceleration. So if we have, and let's get some equations on this. So we have an acceleration of 17.29. That's going to be dv dt. That's definition of acceleration. 17.29. Separate variables and integrate. And we're going to have equation for velocity. That's 17.29 t. Okay, so sweet. So in 10 seconds, we're going to be going, 172 meters per second. So yeah, for sure, we'd be, at this acceleration, you could go over 100 meters per second. Okay, sweet. So yeah, I'm kind of curious now. Like, what is the fastest? This is fastest 0 to 60, but what do dragsters do? Like, what is their dragsters got to have the highest acceleration for the shortest amount of, speed. From 0 to top speed, they must do it in the shortest amount of time. I just don't know how fast these things go. Do they even hit 150? Do they hit 200 miles an hour? I don't know. Alright, so now I think we actually have to just kind of hunker down and do this one. That's a bummer. I thought we were going to pull off some loophole that it was just physically impossible for this thing besides the frictional component. But alright, so now let's lay in. Alright, hell yeah. And so people kind of want me to just solve problems, I mean, every once in a while with like, hey, like I don't know anything about what's going on. But I guess here's where I'm going to start. I'm going to draw the car. Obviously, the friction of the wheels. I mean, I assume at some point we got to draw a circular wheel. But we're just going to say this has mass. Because it has mass, it's near the Earth. The Earth has a huge amount of mass, and it has a center. And so the distance, I mean, you should always write that. The force of gravity, gravitational constant, mass of this, mass of the Earth divided by the radius of the Earth squared. Because from the radius to the center of this object is what we're measuring. Now, if this object was at the International Space Station, we would have to add that in. If it's on Everest, it's about the same. Who cares? Alright, so that's where that comes from. And that's why these three terms, mass of the Earth, gravity, and radius of the Earth squared, are literally just come out to be 10. You know what I mean? This is, I just think the devil for all this. This is 6.67. You can just say 6.66, but close enough, times 10. I don't know how you're going to remember 10 to the negative 11, but mass of the Earth, that should be pretty easy. Or I don't even know what it is. Oh, bummer. Yeah, I'm kind of blanking, but it's 10 to the 24. Is it just 6? Is it 6 times 10 to the... I don't think so. No, I don't think that is. I think it's 2 times 10 to the... No, that's the mass of the sun. Actually, I don't know what the mass of the Earth is, but it's positive. And radius of the Earth is it's 6.37, but it's 6 times 10 to the 6. 6 times 10 to the 6. A lot of 6 going on. Oh, yeah, so, but we square it. So, hell yeah. So, I do think this is 6 times 10 to the 24. Is it? Yeah, that would be interesting. Because here you're going to get 6 times 6 you're going to get 2 6s, and then you're going to get 10 to the 12. Okay, and then here you got a 6 and then a 6. Cool. Yeah, this must be 6. That's why I do this, you know, because then you can't just mess up. And so this is going to be 10 to the 12. But this is 10 to the negative 11, so that's actually 12 plus 11, and we got 10 to the 23 down here. 10 to the 24 divided by 10 to the 23 is 10. So hell yeah. So that's always, if you've never done that one, you know what I mean, go do it. You just, you know, turn everything into 6s, which they're close enough. This is 2 6s because we square it, 6 squared. And hell yeah, this 10 to the 6 goes 10 to 12, add that 11, and you got 10 to the 24 divided by 10 to the 23. I do not know why I just said that twice, but you get 10. You know what I mean? So wait, these three things are 10. And so we get F equals ma. Well, yeah, force of gravity is mass times the gravitational constant. And that's force of gravity is whatever mass we have times 10 meters per second squared. You know what I mean? Or 9.8. You know what I mean? Close enough. All right, so that was the whole deal of just saying, hey, this is mg. You see that a lot. You know what I mean? Maybe you just see it like, hey, the weight is mg. Well, it's the force of gravity, and it's that equation. All right, booyah. And, okay, sweet. So that's going to be the weight. We know that this car wants to go that way. You know, we got 500 meters to travel. Cool. We're going to have a hell of a frictional force. So we have a force of friction. I'm just going to call it, I don't know, F. And this is going to be the coefficient of friction times the normal force. And so here's the normal force with the ground. It's the weight. It's whatever force that's pushing into the ground. And we don't have, like, let's say this was on a, like, if you're, how does this work? Alright, hell yeah, this problem doesn't have any angles, so yeah, so when we sum the forces in this direction, we see that, and we'll just say sum of the forces in the y direction, and this goes from F equals ma. You know, if we identify a force due to, we have an mg, we got a force in that direction, so F equals ma is pretty cool. It says, hey, we've identified a mass, and if we put a force on that mass, so let's put the mass right over here, we put a force on that mass, guess what? It's going to start traveling this way, and it's going to pick up some speed. If its velocity was 0, hey, guess what it's going to be over here? It's going to be some number of velocity. You're going to have a change in velocity. That's this whole acceleration thing. But when we just have a parked car that's ready to go across a bridge, well, it's not sinking into the earth, so what gives? We have identified a force, we have a mass, why don't we have acceleration? Well, is because there's another force over here that's kind of canceling it out, that's equal and opposite. And we're going to call that the normal force. Now, you know what I mean? If we just had the normal force, if we just put a force underneath something and we're no longer on the earth anymore, there's no force of gravity, well, same thing. This chunk of mass is going to go that way, and it's going to keep increasing in speed. Okay, so let's get back to this. These forces cancel, so yeah, we don't get any net force, but we're still identifying forces, and so even if you identify one force, cool, you better start identifying other forces, but you can always just do the eyeballs, you know what I mean? Observe what's happening. If there is no motion in this direction, you can say that the forces in the y direction is that mass times the acceleration in this y direction, and that's 0. And so, sweet. So now this side of the equation is the forces, so we're going to say we have an mg, and I guess we're going to say this is the down direction, so we have negative mg plus a normal force up is equal to 0. Cool, so now we can see that n, get the mg over there, is equal to mg. This normal force right here is equal to mg. Oh, okay, because this equation for friction has n in it. So now we can say this friction, this force of friction, I'm going to do ff. Force of friction is mu times mg. Okay, hell yeah. And now we can say that the force of friction, because they were saying the coefficient of friction is 1, And so we're going to have the force of friction is just mg. Okay. Alright, hell yeah. So, like, I don't even know what this means. You know what I mean? Like, what does the force of friction, what does the coefficient of 1 mean? You know what I mean? It means that the force needed to overcome... Oh, so there you go. Well, the force needed to overcome... Oh, I got it. Yeah, so it does go back to this. I'm so glad we did get to the high end. Yeah, and we did solve for this one. We solved for the fastest car in the world is pulling 1.7 Gs. This is such a cool problem because it reminds me, my brother is smarter than I am. And he brought up, let me grab a sheet of paper because this is going to be hella cool. And this is related now. So I see where this problem is going. So you can find, this is such a cool thing to do. It's like if you're on a cliff about that big and you're about that big. Okay, and then you have a hell of a long pole, in your hands. You know what I mean? But the pole is only that long, and then you got to drop like that far. And so there you go. So you're going to be falling, and then once this hits, like you fall through the air. So let's pop over here, same cliff, but now the stick is on the ground, and then you are just right here. Now the question is, like what's the limits of this? And this is really cool. Because it's identical to what the problem says. My brother said, let's say at the gym, here's the ceiling, and they have like a steel pole, you know what I mean, that's just kind of hanging there, and maybe they have like a rope to get up to it, okay? And then so you climb the rope, and then you, with your hands, hold on with your body weight to that steel pole. All right? I think we could all do that, and we would be totally chill. Okay, so now, because like I'm leading you, the aha moment should be coming. So now at this same gym, they have on the ground a huge chunk of weight. You know what I mean? It's kind of like a bar, just a pumpkin-sized chunk of steel. And it also has a pole sticking out of it. And it's like, hey, like your objective is to lift this off the ground. Okay, so you can visualize that. Now, let's say a person weighs 200 pounds. Like, just use your imagination and ask yourself, like, what's the strongest person that weighs 200 pounds? You know what I mean? Whether they're a weightlifter, a boxer, you know what I mean? How much force, like how much weight do you think they could lift off the ground? Like, I'm just going to say 400 pounds. And that's probably way overshot. But I'm just getting this because we're saying it's just double. Like a person could lift, or do it this way. You know what I mean? Let's say this person is on this kind of cliff right here. And same scenario, this huge weight. And then this weight is also attached to a rope. And then you have a couple people on the ground, like maybe 3 or 4 people, that are letting this rope, slowly letting go of this. So all your objective is just to be able to not make it slip through your hands. It's not how, in this case, it's how strong you are. You have to, one, actually lift the darn thing. But in this case, what's your limit? Like, hey, if this weight is so strong, I mean, if this weight is so, let's make it less phallic. Holy hell. All right, so we have a brick of weight here. So in this case, what's going to happen is you're just going to have to let go. You know what I mean? And that letting go process is because, well, I don't know, like your limbs are about ready to rip out of your arms, but it's because your fingers are slipping. You know what I mean? Slip. You can't hold on to this. Okay, so there's the limit. Is like, hey, I think we could all hold on to our body weight. And so this is really cool because it explains why this works and what's the limitations. If we can say we can hold on to our body weight with our fingers, we can apply a pressure of well, and then it also is just like making sure your limbs don't like rip off, because you could just literally strap your arms to this and then like strap your back to like a, you know, and then just rip your arms off. They could just let this rope go and your arms would literally rip off. You know what I mean? So there's that aspect too. So there's kind of this limit of like, hey, I could hold on stronger, but I would just tear my arms. You know what I mean? Yeah. But then there's just, hey, if I have a steel pole, I can provide enough friction to at least hold my body weight. And so let's go back to this scenario. And this is holding 1G. I don't know. I think I wanted to, you know, use way more words to get to that. You know, it's like, why is that holding 1G? It's because, oh, this is cool. Because even right here, with a slick pole, you know what I mean? So let's draw the pole again. Hey, like there's no little chunks out of it, you know, to like actually get your, like friction is just micro chunks at a smaller level. But it's still, that's why when we do coefficients of friction, I mean, we just have to run a test. Because, yeah, there is micro things that are gripping, you know what I mean? And those things grip even while it's moving. That's going to be kinetic friction. Or if it's static, you know what I mean, right off the bat. Now, the cool thing about a car wheel is that every time the wheel rolls, because of rolling motion, hey, this point actually stops. There's zero velocity every time your wheel hits a new portion of your wheel does hit the road. But it's stationary. Everything else is rolling on top, but the point that hits the wheel is actually not moving. It's not shearing like relative to the road. That point does not move. It just touches the road and then just acts as a tipping point and then moves on. So there is no, this wheel isn't sliding this way. All right, hell yeah, we're almost there. Oh, and the person sending this to me is just like, hell, get on with it. I'll make kind of a shorter addendum at the beginning. But yeah, this is cool. I just want to explore this concept, and like my mind isn't like 100%. You know what I mean? It's just really hard to think of things and then do the kind of the investigation. But sweet. So when we have this downward force, the only friction we have is just this direction. So we can put a force. We can put a force into it. It's the same thing as our weight. We can squeeze it. This is synonymous with weight. This is synonymous with anyway. And then so we have a coefficient of friction. Now this is where, in this case, I guess, you know, you want your coefficient of friction to be something where I'm just gonna use the, hey, it's 1. If your coefficient of friction is 1, then of kinetic friction, man, I'm having a hard time. But we got mu times the normal force, and the normal force in this case is the weight. I don't know. It's not the weight of you though, so that's kind of weird. It's just the clamping force, like the force clamping of your hands. So that's going to be mu force clamping, and And if mu is 1, well, oh man, it's also not, is that not representative? Huh. Oh no, because, because, this says that if we have a weight of mg, and then and the coefficient of friction, if we're just holding on to this and not moving, cool, we have an mg, our weight's going down, and then we must have a normal, we must have a friction. This is the force of friction. This is the frictional force. That's mu n. That's going to be a coefficient of 1. And it must, because these forces have to equal, let's do so we have, let's do sum of the forces in the y is equal to 0. So we have negative mg plus force of friction has to equal 0. Cool. So we're going to say force of friction is equal to mg. We're going to say that force of friction is mu times the force, clamping force that we can use with our hands, and that's going to be equal to mg. We're going to say this coefficient is 1, so we're saying the clamping force of our hands has to equal our weight in mg. So the clamping force has to equal our weight. Cool. Now there's a chance that so this would be a coefficient of 1. Now in this game, when you use a pole, like I said, you could make it full of sandpaper. It could be actually like little grippy fish hooks that like literally your skin and arms and your whole body could rip off before you actually start to slide down it. So keep that in mind. But for a pole that you actually want to slide down, but you're still providing that friction, you know what I mean? I think this is a good target. If you do this sport of jumping off a big cliff with a pole, because there's a lot of consequences. You might mess it up and then tip over. But the objective is now you have a hella speed. Let's say you do have a free fall of 1 second. So this is kind of cool because you could, like 5 meters. So your pole is going to be 5 meters. And you could jump off something 10 meters. That's substantial. That's 30 feet. And so if we go back to the original, hey, jumping off a cliff, I always do this one. Velocity is 0. All right, hell yeah. Sorry about that. Acceleration of gravity is 10. So in 1 second, you'll be going 10 meters per second. Your average speed is 5, so you just went 5 meters. Okay, and then to slow down, you have a speed of 10 meters per second. But we just said that you can only, you can only slow yourself down. You can only pull 1g. You know what I mean? You can't, You can't, in this method, in this sport, I don't think you could, because it's not static friction, hell yeah, you could probably statically pull 2Gs, but man, because you're sliding down the pole, your friction force, you can probably only put this amount of force hanging, you know what I mean? And so, okay, hell yeah. So what does that mean? Alright, hell yeah. So this is a little bit mind-melting for me. But yeah, if we get up to 10 meters per second in this scenario, so our velocity is 10 meters per second, and then we hit the ground with 0 velocity, 0 meters per second, well, and we're going to do that in 1 second, that's going to be an acceleration of 10, or negative 10 in this case, but 10, and so it's, and we're providing that acceleration because we are putting the clamping force on here. It seems like, I think I have this wrong, like mentally it seems like if you can apply 1g of force, like you're just going to have a constant speed. Like you got up to 10 meters per second, and so now you're not, I mean, you're just going to hit the ground at 10 meters per second. Like you're not increasing your speed. Because if you, but that's not true either, because in free fall, there's more to this than meets the eye. Because in free fall, the second you're going 15 meters and then hitting the water. And so, yeah. Yeah, oh, this is a good physics one. Because sometimes I like to think that you're turning on and off gravity. Sorry we're spending so long on this one. But it is a good one to get the fundamentals. So we're going to jump off this cliff for a second. We're going to travel 5 meters, which is substantial. It's like 15, 20 feet. Our stick is going to hit, and then we're just going to shut off gravity. Cool. If gravity is shut off, we're just going to continue going 10 meters per second. If we didn't hold on to the pole, we're just going to go 10 meters per second until we hit the ground at 10 meters per second. But if we put friction into the pole where we slow from 10 to 0, that is applying a force just due to G. But that's if gravity is shut off. If you're just traveling through space with this pole at 10 meters per second, and then you come up against something, a massless planet, something that physically just stops, your pole, and then you're going to use friction to slide down that pole to get 0 speed. Your body is going to feel 1G, and you're going to have to generate that 1G by squeezing. I think we just did that. And if the coefficient of friction is 0, you're actually going to have to squeeze. You're going to have a squeezing force of your body weight. But we know you can have a squeezing force of your body weight from this diagram. This exists in real life. You could have a pole and just hang from it. Your squeezing force, that's not 100% true. This coefficient of friction could be higher than 1. I mean, could be lower than 1. Or higher than... Wait, can the coefficient of friction be higher than 1? I think so. Because, especially static friction. Because the coefficient of static friction, if this is 1, it says, well, if you added 2 people, if someone like, hey, it's like a movie scene. It's just like, hey, I'm hanging on right there. But now you're going to slip because the coefficient of friction, if this is an icicle where you physically just can't put enough pressure to hold yourself, doubling your weight is going to make you slip. But we came up with this scenario. Man, sorry we're spending so long on this. We came up with this scenario where actually someone just literally staples or nails your hands to this, and you're kind of stuck like that. Well, hell yeah, you just hella increased your coefficient of friction. You could probably hold 3 people before your arms ripped off. Maybe 4 or 5 before your arms ripped off. Kind of gory, but it shows that, hopefully I don't have that just screaming wrong, that the coefficient of friction could be greater than 1. Even the coefficient of static friction. Coefficient of static friction means to get any sort of movement, you have to overcome this force. That means the force this way has to equal that force. And if this this is due to the normal force plus staples, this could be sky's the limit. 10, 100, I think. Okay, hell yeah. So, man, I thought that tangent was going to really solidify, but it was kind of confusing. The mechanics of this sport is very fascinating. You have to be able to hold more than 1G. So I think the story was my brother said, well, could you hold twice your body weight? And that's true. Could you have this scenario? All right, hell yeah. So my camera cut out, but man, I'm pumped. Yeah, I think we can just do this one now. You know what I mean? So we've kind of figured out that what this concept of the coefficient of friction of 1 means, that in order to move the weight, you know what I mean? So if holy Toledo, yeah, if I can only hold my body weight, I mean, even just saying that, if I can only hold my body weight, I don't have to put another person. I can just, someone puts a couple pounds, throws me a water bottle or something, and it gets caught in my shirt. But if I can only hold my body weight, but then a couple pounds more is when I slip. Hey, that's when I slip. So I think I'm pretty sound on that. You know what I mean? Like I said, though, I have no idea. And I was thinking, hell no, we're not going to put the answer to this in the beginning, because I probably won't even get it right. Because I'm still interested. So this whole idea, yeah. So I would do the drag racer. The drag racer has big old wheels like this, and they're just underinflated. And then when the thing gets going, this wheel starts to just collapse in on itself, because you're throwing, the motor's going, this is going hella velocity. I mean, this is like when they drop the gate, or like the lights go to green or whatever, hell yeah, this happens. The engine turns, this wheel starts to turn, but this position, I mean, the actual car isn't moving yet. The car is just, man, I don't want to draw anything phallic. Anyway, the car isn't moving, and but guess what? This wheel actually is starting to turn. But if this wheel turns once, the car will move that location. But you have this underinflated tire that just like overlaps on itself, and so that's kind of what happens. And so you can get velocity coming in, and then that velocity has places to go, building friction. And so, man, this is, for whatever reason, it's hard on my brain. If I have a, yeah, and this was interesting. So I just looked up, this is driving me nuts, this kind of looks phallic. I just looked up rocket propulsion, and that first chapter in that physics book, basically says, hey, a car has to crawl its way. A car is literally like crawling, feet and hands crawling along a roadway. It's gripping the roadway. And so if you actually look at this is kind of cool. So this is like Einsteinian. I think there's a book called like Einstein's Dreams, and maybe I just dreamt that. But it's all these different worlds where, hey, maybe you have a planet that's about the size of you, and you're just floating on it in space. And so guess what? I mean, this is actually really cool, because I could totally visualize this. So you're just clawing to this planet. Hopefully you don't jump off of it, because else you just float along the galaxy. But you're just clawing to this planet. And let's say you want to get to over here. Well, and while you crawl, let's say this planet is really lightweight. It's kind of this shell, and this planet has the same mass as you. You know what I mean? It's kind of your equal and opposite. And so if this planet has the same mass as you, and you crawl to this point, that point is basically coming to, bummer. I don't want to say anything I don't know. Do you get to the halfway point? That would be another good problem. It's like, do you get to the halfway point, or does this point just come underneath you? Like you're like, from your perspective, you're crawling towards it. You see that. But from the observer's perspective down, it's like, no, all we saw was that X was traveling towards you. You were kind of doing it's kind of almost like a video game. You're kind of just doing the MC. They don't call it MC. I don't know what they call those video games. But anyway, and then the ground is coming towards you. So it's the same thing that happens on the Earth. You are a mass, and if you want to push the Earth that way, sure, you're going to go that way. Or if you do go that way, laying down friction with your feet or with wheels, with a wheel. You get to go this way, hell yeah, but only at the expense of the earth going that way. And so this is super cool because I'm not going to get, because this is helping me actually get to this answer. In that first chapter, that book said, it said the center of mass of the rocket ship never changes. And that kind of blew my mind. So let's say you have a rocket ship. Oh, damn it. I'm just going to draw more. That's the only thing about engineering. I just remember being in engineering class, and the teacher just has a hell of a time. You can just totally tell. So everything in engineering is literally... okay, so you have a rocket ship. Now, I wish I didn't draw those, but here's the boosters, or here's where the fuel gets expelled at a high rate of speed. And so we're just going to pretend that this rocket is just in space, and for whatever reason it has a velocity of 0. Like something was able to put it in... I don't even know what that would mean, having a velocity of 0 in space. Everything is going around you. It's like, well, it's like that's also an interesting question to visualize. Could you have 0 velocity in space? Because not really. Everything else, I don't know. But anyway, so we're just going to visualize it has 0 velocity relative to its position currently. Cool. And so we're going to say one atom. So we have, whatever atom of fuel, and when we got the electrons going around, and so we're going to say only one. So this atom used to be right there, inside the fuel. Like we're just saying, it's just like right before combustion. It's almost at the end, and so we're going to say the center of mass is right here. Okay, hell yeah. And how does this work? No, this will work really well. So, and then we're going to, at the speed of ignition, or the speed of how gases expel out of a rocket, this atom goes hella fast that way. And so now this atom is hella over here. And guess what? From this point in space... Now I'm just measuring. Sorry, I didn't line it up very well. Now I'm just measuring. Now I'm actually taking, like, I'm like, for whatever reason I'm able to pin a point in space and be like, hey, this is your center of mass. But because you have that thing going that way, your center of mass doesn't change from this. This is bizarre. Like literally, if you get a full rocket up into space and then place it there and then start up the ignition, the mass going this way and the rocket going that way, the center of mass right before ignition will be the center of mass of all molecules in that system. And I find that incredibly fascinating. As long as this doesn't change direction, as long as it keeps going that way, it wouldn't matter like how many times you turn on and off the rockets, like when you do that. But that is such a weird fundamental that I just thought it would be very fascinating doing it with just one atom. Because it simulates what happens when you crawl across the ground. Like the Earth, like you're going that way, sure, but the Earth is actually going that way. And it's synonymous with center of mass. Even though you kind of have this, like Earth is like kind of a sphere that's like held in space. And sure, if you're going this way, the Earth has to go back that way. But yeah, it has to go back that way in equal amounts of conservation of mass and velocity. So that's totally not, I don't think, what this problem even has to get into. But because your mass started to move, hell yeah, the Earth has to go the other direction. And it would make more sense, not a person, but just a car. and we're just going to say a car driving at a constant speed. Because now you have, or does that make sense? Or does that make even less sense? Man, I love it when I don't know stuff. But yeah, if a car goes at a constant speed, then is it needing to grip the road? I don't think so. I think, like, if you have an earth and the car stopped, hell yeah, and then from here to here you get up to your constant speed. For the amount of change in momentum, your change in velocity, you are a mass. So that's the definition of momentum. Momentum is mass times change in velocity. And so you change that. And so the momentum of the Earth has to change. But the momentum of the Earth is... The Earth isn't just like, hey, a mass on a stick. You know, it's got tons of mass everywhere. So if we start to roll the Earth backwards, every little particle of this mass moves backwards. So the Earth will hardly move backwards detectably at all just because a car started to get up to speed. But Newtonian mechanics says this is at play, like 100%. Like you are moving the Earth just walking along it. So if the Earth from a north perspective, I think I've done this before, is spinning that way. If you're looking North Pole down, and then you start to walk, well, if I walk this way, the Earth is going to, if I walk this way, the Earth is going to go the opposite way. So if the Earth is going this, oh, yeah, so if I walk this way on the Earth has to go... So you could stop if the Earth's going around the... So if you're at the equator and you're facing away from... You're facing the sunrise because that's the direction that you're traveling. The sun is catching you. Walk towards the sunrise and you will slow down the Earth. So that is kind of a cool perspective, but man, it's just mentally difficult to kind of see and understand. Anyway. All right, hell yeah. Does that help us at all? No, let's get back to this one. So we have this imaginary center of mass at time 0. This molecule goes that way just for infinity. You know, it's constantly going that way, but because it got expelled from this rocket now has some tangible velocity. And so the rocket is now going this way, imperceptibly, but the center of mass of this system will always remain at this fixed point. If this rocket, because that atom, just one atom, got expelled, if eons later this rocket makes it to, to here, and cool, we know where the hell that atom is, because we know the center of mass. So it's kind of fascinating. You could almost set up an experiment like this by making a heavy thing, I don't know. But anyway, so let's move on because we need to actually get back to the problem at hand. Alright, hell yeah. So, and I'm getting closer because we have this idea, okay, something's at rest. So we have something at rest, 0 meters per second. The only way we can change its velocity is to input some sort of acceleration. We have an acceleration. And we know from F equals ma, that's going to take a force because we've identified a mass and we want it to change its velocity. So we have to input a force. Okay, if we do input a force, we rearrange this equation, we say force divided by that mass. This will give us the change in velocity for every second. Change in velocity, change in time. Usually in units of meters per second per second. And if you write it like this, hell yeah, that is definitionally going to be your change in velocity every second. And for car problems or rocket problems, that's great because you might be accelerating for a longer period of time compared to like a mechanical thing that, that's spinning, it might be spinning at 1,000, revolutions per minute. 17 rounds per second. We've done that problem before. Alright, hell yeah. So, what are we getting at? Yeah, so you must impart... So yeah, if something is at zero velocity, like this, the car started from rest, you must have changed its velocity to actually get it up to speed. And the definition of change in velocity is... Or change in velocity, change in time, is acceleration. So, and we know, that's why I came at this problem from the perspective of like, hey, humans cannot pull 3 Gs. 3 Gs would be an acceleration of 30 meters per second, you know what I mean? Because 10 is gravity, 3 times that is 30 meters per second. But we saw that the fastest car is pulling 1.7 Gs. Okay, hell yeah. But now it goes back to this. Like this crumpled up rubber has a coefficient of friction of more than 1. And I'm not going to look it up. Even after posting this video, then I'll look it up. But I'm not going to re-edit this video. Because this video is teaching me, right now it's like, can we have a coefficient of friction? And we're just dealing with static friction. Even though the car is moving, we went over that. It's always static with the ground. There's no movement, even though the wheel's moving. But hell yeah, so I think we've mastered the fact that you can have a coefficient of static friction of more than 1, because the second you staple your hands to like a wooden pole or something, I don't know, you can rip your arms off before the friction would ever give. Alright, so hell yeah, so with this dragster, you're going to get, hell yeah, more friction, because your acceleration, that's so fascinating to me. Acceleration of that fastest car off the internet, this Google one, was pulling 1.7 Gs. That's the acceleration was 17. So for a dragster, maybe you could pull 20, I'm just going to guess, 28 Gs, 2.8 Gs. Maybe you could pull 3 Gs. That was kind of the upper limit, because an amusement park ride could be 3 Gs, you know what I mean? And the human body can't sustain more than, you don't really want to exceed 3 Gs. That's kind of your limit for just kind of normal space travel. That's kind of what they're shooting for. Nothing more than 3 Gs. Okay. So maybe I'd be curious to see if a dragster can pull 3 Gs. But that means that this coefficient of static friction, does that mean it's just 3? Is that fundamentally what's that saying? Oh man, I kind of just want to solve this problem from a fundamental perspective. Just being like, because this part, I'm still just like, well, I get kind of, I think we've proved it, but just kind of in a roundabout way, that if your coefficient of friction is 1 with the ground, which is static, meaning that if you're crawling your way across the ground, your palms are going to slip. That's a good way to look at it. If I'm on an icy surface, just like the hockey rink, but it's all like slippery as can be, kind of wet and stuff. And all right, hell yeah. No, this is so fascinating. Yeah, because it's what the wheel is kind of like whooping something up to speed as well. Like the wheel is like basically crawling its way across the ground, and every time the wheel kind of makes contact with the ground, it's like hell yeah. And then the car can go, and especially if it's going faster, if you can keep putting this force, because that's okay. Yeah, let's talk about the limitations of this, or the limits of it. If we have a road, and so yeah, and we can put this the force of friction. And see, I drew it the wrong way, so that's so fascinating. It just shows really my limitations in this. I hella drew this the wrong way. The force of friction going that way. No. we're literally like crawling, putting our hands on the road, and then making our hands go this way to try to slide. It would be like, so I'm going to draw this just real fast. We have a skateboarder, and you're on a skateboard, and your hands are out to the side, and you're crawling your way along along the ground. Okay, so you are doing this with your hand across the ground, and because your hand sticks, that means that the force of friction is that way, right? And I really don't care about that part. You know what I mean? Because I think we basically solved the problem. Is that to go? So let's just do it. To go 500 meters in 10 seconds has an average velocity of 50 meters per second. You're starting out at 0, so your end velocity must be 100 meters per second. You must have had a change in velocity of 100 meters per second in 10 seconds. And so you're pulling. Yeah, so your acceleration is 10 meters per second, and which is 1g. And so and that's what you would expect if your coefficient of friction is 1. So that's the relationship they're getting. So but I'm glad I did all the lead up. You know what I mean? Just tried to learn as much as possible before, you know, kind of tackling the problem. So that's what it was in a kind of a 3-second synopsis. So this problem, and it hits those things like, hey, you have 0 velocity, but to go all the way, you know, 500 meters must mean you've had in 10 seconds your average velocity. So you got to get that first. That's 500 meters divided by 10. That's 50 meters per second. But because you started at 0, to actually do that in 10 seconds, your final velocity has to be double that at 100 meters per second. So if our acceleration is constant, you see that we have a change in velocity of 100 meters per second, but our time frame on it is 10 seconds, so that gives us an acceleration of 10 meters per second squared. Change in velocity of 10 meters per second for every 1 second. And I'm just kind of bummed that I don't even know which way to draw the friction. You know, that's messing with me. Because, yeah, I would assume you would draw the friction. You would draw the frictional force. I don't know. I don't know, honestly. But my knowledge is I know what mu of 1 is. You know what I mean? And so if this was increased to 2, you would be able to do it in a shorter amount of time. You would be able to pull 2 Gs. Your acceleration would be 20. So let's say you could do that. If mu was 2, you could go from 0 to 200 meters per second. That could be your change in velocity in 10 seconds. You'd have an average velocity of 100 meters per second. You know, always kind of doing the working backwards. And if you had an average velocity of 100 meters per second and all you're going is 500, so you would take 500 meters divided by 100 meters per second, you could do that in 5 seconds. Alright, hell yeah. So I'm bummed that I don't know what direction the frictional force goes. But yeah, let's finish the video on that, because if this is our dragster, the mass of the dragster goes that way. For the mass of the dragster to go from 0 velocity to some velocity, it has to have a force that way. And so, if it has a force that way, Yeah, it's so bizarre. It's just like, how does it get that force that way? Oh, I think it is kind of more complicated. I think you have to take the whole Earth into consideration. Like, you're literally pushing off the Earth for you to go in that direction. And that's kind of the hard thing to, like, visualize for me. And so, yeah, I'm just going to call it at that, I think. You know what I mean? I know where I need now to spend more time and kind of like, well, how, if the wheel's gripping the, yeah, because I get how the wheel can be kind of separate from the system. The wheel is the thing, almost like a paddle boat with paddles. The boat's floating on the water, but then this thing is pushing the water, kind of gripping and pushing the water that way. And then so I just don't know which way to draw I mean, if there is a net force this way that we're generating on this mass, on the car, but that net force can only equal mu n, then if this force is that way, the frictional force should be this way. So I think I drew it right the first time, I just have no idea, So, yeah, I feel like I drew the frictional force this way. I just don't know why. I apologize about that. But there you go. So it's an incomplete answer. So maybe I will actually go to the computer and figure out what's wrong with that. And I probably, I don't know if I'm going to make something at the beginning, because this is such a damn long video. And so, yeah, I don't think so. I think we're gonna do what we did. I might reference where I solved this, but I think all the lead up is most important. I think I'm gonna title this one as just like, hey, can you solve this problem faster than me? And I'm sure anyone could. All right, so hell yeah, I think we did it. Thanks for joining me. And guess what? That's a video. But yeah, let's finish the video on that, because if this is our dragster, the mass of the dragster goes that way. For the mass of the dragster to go from 0 velocity to some velocity, it has to have a force that way. And so, if it has a force that way, yeah, it's so bizarre. It's just like, how does it get that force that way? Oh, I think it is kind of more complicated. I think you have to take the whole Earth into consideration. Like, you're literally pushing off the Earth for you to go in that direction. And that's kind of the hard thing to, like, visualize for me. And so, yeah, I'm just going to call it at that, I think. You know what I mean? I know where I need now to spend more time and kind of like, well, how, if the wheel's gripping the, yeah, because I get how the wheel can be kind of separate from the system. The wheel is the thing, almost like a paddle boat with paddles. The boat's floating on the water, but then this thing is pushing the water, kind of gripping and pushing the water that way. And then so, I just don't know which way to draw I mean, if there is a net force this way, that we're generating on this mass, on the car, but that net force can only equal mu n, then if this force is that way, the frictional force should be this way. So I think I drew it right the first time, I just have no idea, So, yeah, I feel like I drew the frictional force this way. I just don't know why. I apologize about that. But there you go. So it's an incomplete answer. So maybe I will actually go to the computer and figure out what's wrong with that. And I probably, I don't know if I'm going to make something at the beginning, because this is such a damn long video. And so, yeah, I don't think so. I think we're going to do what we did. I might reference where I solve this. But I think all the lead up is most important. I think I'm going to title this one as just like, hey, can you solve this problem faster than me? And I'm sure anyone could. Alright, so hell yeah, I think we did it. Thanks for joining me. And guess what? That's a video. Alright, hell yeah, we can't end the video there because this is really important. Man, this is kind of blowing my mind because I was just like, well, hell yeah. So let's see if you have like a person that's kind of got their legs out off the ground, and what they're going to do is they're going to push off the ground, basically just lifting themselves off the ground. You know what I mean? And so hell yeah, we got that person, and they used to be on the ground like sitting, but now they just lifted themselves off the ground. So where's the force? This is the wild thing, is that you're putting a force into the ground. You're putting a force in the downward direction. So cool. So the simple part of this is like, well, how are you going upward? Because if we said that your velocity was 0, and then at some point, and that's the other thing for these problems, I mean, don't think of the whole cycle of like lifting myself off the ground and then coming to rest at the top. Just kind of do like the first split second. You used to have 0 velocity, and now with a force, if you moved off the ground, you must have some sort of velocity. And so just leave it at that and know that we have a change in velocity, we have an acceleration. F equals ma. If we can visualize that we have a change in position, and we knew we were at rest, we must have acceleration. We are a mass, and so a force was needed to do that. And then kind of the free body diagram is like, take this system and put it into outer space, and if we see, visually, what happened on the Earth, we must have had a net force this direction. And so that's kind of the wild, the wildness of it. And so, yeah, and then let's take a look at this. When this happens, because this is dynamics. It's no longer a statics problem. So we're a mass, and we have the Earth right here. We're going to sum the forces in the y direction. And so, and guess what? They're not going to be equal 0, because for this split second, we have motion, we have acceleration. So we're going to say this is equal to ma. So we can sum the forces. Down in the downward direction, we still have the negative mg due to the force of gravity, the attraction between two masses. One is huge, it's the Earth, but we're really far away. We're on the radius of the Earth. Cool. So we have negative mg. The other is this force that we're pushing. So we're just going to say, hey, both arms are just one number, and we're going to say that's F. So we're going to say plus F. That's going to be, did I get this right? No, I feel like I'm messing up still. Alright, man, I feel like I'm horrible at this. Usually I have kind of ways to overcome this, but basically what's going to happen is that we're going to have a normal force. Yeah, okay, that's right, because, yeah, sure, we're putting a force down, but I think when we draw the free body diagram, when we chop ourselves and put us, like, we consider ourselves not attached to the Earth, and so we say, hey, we're going to have a net force in this direction, so what gives? We're going to say through our center of mass we have mg, that's in the downward direction. But now the only other mass is what's the force of where we're touching the Earth. And so that is a force, that's the normal force. Alright, hell yeah. I feel like I'm horrible at this, but I still, yeah, and maybe, yeah, this is interesting. Yep. I think there's a lot going on here because let's say maybe like my arms aren't moving, and so like the force is kind of like from this part, up. But yeah, it is fascinating. But I guess if you want to lift yourself off the ground, I guess the take-home point is the force that you push into the ground has to be greater than your weight. So that's what's happening. If you're putting a bigger force into the ground that's greater than your weight, what happens is the normal force is increased, and it's the normal force, that larger number is larger than this, so you're going to have a net force up and you're going to have an acceleration up. So holy hell, I thought that was going to be useful for, well, let's do one more. Because let's say you were in space, kind of like on and then you're just next to kind of a ladder, kind of like a space ladder, and you're just floating. Let's see if we can do this. And let's say you want to go up, like you want your mass to accelerate up. Cool. What you're going to do is you're going to grab that rung and push down. Once you push down with your hand on this rung, your mass is going to go up. You're going to accelerate in that direction. So let's go back to the road, because that's all I wanted to do was just like, well, how do we explain this road? And in this, let's say this ladder just feels like it's just rigidly attached to the universe. Cool. That's the same thing with the Earth, even though like nothing's really attached to anything. So if you go up, this ladder is actually going to go that direction. And so, but let's say it's attached to the Earth, and this is a space ladder that you can climb up, and you're actually still floating. Next to it, because it's so high, you're just in you're freely floating, but you're still going to push down to like move your freely floating body up. So we got that. And when you do so, the Earth is going to go in the opposite direction. For the life of me, I'm just struggling with the free body diagram perspective. Okay, but the same thing happens here. Is the wheels are gripping the road. So like just pretend like this is rungs on the ladder. And same thing, the car wants to go this way. And so you're taking this and you're putting a force that direction. So this is the force that you're putting, laying down with your car wheels. But you can only... So now let's say when you push down on this rung, the rung breaks. Because it's just made of... I was going to name drop, but we won't make any jokes. It's made from whoever makes crappy stuff. You know what I mean? No, I'm just joking. But anyway, so yeah, you pull down on that rung and it breaks. And, that's the equivalent of the frictional force no longer giving. So, yeah, hell yeah. Yeah, there's no difference that if you're crawling across an ice rink and there's a chunk of ice that you can actually get your fingers on, and then put a force that way with, and that's going to make your mass go this way. That's the only thing. Why am I struggling with like an equal and opposite? If you put a force this way, I guess it's just it's almost, this is the conservation of momentum. I think that's why it's tricky. It's like this is the other one that I do. I'm just surprised that when you're on Earth, all this conservation momentum still applies. Because if you are a floating baseball player, let's say you're floating in space, okay, and then you have always done this one. You have like a sack of baseballs. You have 100 baseballs. Cool, and you have zero velocity. Well, guess what? Let's say safety is like here's your ship that you fell out of. And it's just right over there. So you're just going to start throwing baseballs this direction, and you're going to slowly start moving that way. So we've done a lot from this problem. One, we've established that your center of mass will always be right here. But you'll have to throw a bunch of baseballs that way. You just have to throw one baseball that way, actually, and then just wait for your velocity to slowly carry you to your spaceship, also zero velocity. But yeah, we've learned a lot, but we've learned that, hell yeah, you got to do, so let's get back to this scenario, because yeah, it's a ladder in outer space. If you have a ladder this way that's floating in outer, I love doing stuff in outer space because everything works like that. And then and you have a, so this is the mass of the ladder, and then you made a small car that weighs the same amount as the ladder, and the car is like just going on like the rails of the ladder, and it's actually a cogged ladder, you know what I mean? So, and then your wheels are cogged. You see, you have and if the car's got 0 velocity, if the car starts moving that way, the ladder will equally move that way. The center of mass of this system won't change. See, now my mind reels because it's just like, well, will the ladder move at the same speed? You know, because then I would have to make the ladder like 1,000,000 miles long and be like, well, is it moving at the same, you know? Because no, it's not moving at the same speed. It depends on how much does it, I think, I'm just going to go out on a limb here. If this is the mass of the car from this length to this length, and the mass of this ladder is from that length to that length is the same proportionally. No, I have no idea. Man, I'm gonna struggle with the actual center of mass deal. But that's what's going on with this problem. We're applying a gripping force this way, kind of equal and opposite. Yeah, in a sense, yeah, this is wild. Let's draw the Earth. In a sense, you're trying to push the Earth that way underneath you so you can go that way. And you do apply a force, but the mass of the Earth is just huge. And then so you actually travel a lot faster when you do that. And the mass, the outside of the Earth doesn't feel a darn thing. But you are having, yeah, I kind of want to, yeah, don't have any, yeah, there we go, a couple more. So yeah, this is fascinating to me. Just to visualize it. All right, Haley, I'm glad I did this, and know for sure that no, the speed of this ladder isn't going to be the same as the car, but the center of mass, that's the principle here. If the velocity is 0 and the car's on this ladder, however long it is, when the center of mass is right here, as this car goes that way, the center of mass won't change. So the amount of ladder that needs to go that way to keep the center of mass right here, and I'm sure there's some symmetry here where we could figure out how much mass, like if you know, this much mass went that way, then that much of the ladder had to go that way. But that's wild to me that a car driving across this bridge is actually making the Earth go the other direction. Like molecules on the Earth are going the other direction, just a fraction of an amount. It's so minuscule, but it is there. Newtonian mechanics are fascinating. So I was just telling my brother, it's just like everything that's made of an atom cannot disobey Newtonian mechanics. So I think that's the most fascinating thing about this whole problem, is that when the car starts at rest on one side of the bridge and decides to hella accelerate the entire time for 10 seconds, the Earth is literally... okay, so no, and I can explain this. So let's make the car just a chunk of mass that's that size, like relative to the Earth. Cool. And it starts to accelerate for 10 seconds. Every part... so you could say there's a molecule on the Earth that also accelerates for that same amount of time for 10 seconds. That weighs the same amount as that car, that actually traveled the same distance. But we know that's not the case. But this is the cool thing with, because I guess if you're doing this problem, I don't know. You definitely are doing rotational inertia. Maybe you're not. Maybe people aren't teaching this for that purpose. But what happens when something is rotated? When this car goes this way over the... Sorry, I didn't draw this close enough. But this car is actually attached to the Earth, and it drives along the Earth for 10 seconds. So let's just draw that in. So this mass goes this way for 10 seconds. Because this Earth is made up of so many chunks of mass, this Earth does roll back that direction by a small amount. And it keeps doing so. If we're applying a constant acceleration, that means we're applying a constant force to this Earth. That means this force is experiencing a constant angular acceleration. Like an I alpha. Those terms come in. But this I term accounts for every molecule on this Earth and a slight change. Like the molecules at the center aren't moving at all. You know what I mean? So those aren't moving. But every molecule moves, where if you summed up all those molecules and then summed up all their movements and averaged them, you would have a mass brick the same size as that car, and the distance they traveled would be the same distance. They would have the same change in velocity for that 10 seconds. So that's kind of the take-home point. That it's kind of that's literally, what is that, the second rule of Fight Club? Newtonian mechanics is the equal and opposite forces. Like, the only way that you're going hella fast doing anything, even if it's, is the fact that, like something else is going the other direction. Even when you're skiing down a hill, like you jump off a cliff onto the Earth and hit some powder and be like, hell yeah. Well, guess what? The Earth just went that way. And then once you, take your body up to the top of the lift, hey, the Earth, some of these are just mind games. But yeah, this principle does apply. It's just weird that the Earth is so big and we don't see that, like, hey, I'm going this way, everything else is going the other way scenario. But we did it. And we did it from the perspective that, so we have the car, and it has to apply a force, on that ladder, kind of that fictional ladder, and it's got to apply that force this way. But the force of friction, man, I hope I get this right. So I think the force of friction is that way. I'm not quite sure. That's the only thing. I thought I could start this video again and explain the force of friction, but I'm glad I started it to do kind of relative, relative motion, or like, equal and opposite forces. And it's conservation of momentum. Like, you have to have a conservation of momentum. Like, if you're a baseball pitcher out in outer space with a bag of baseballs, you throw a mass this way. Well, cool. You're going to go that way. Your center of mass will always stay the same. I think that's very fascinating. Alright, hell yeah. So I really didn't explain what direction the frictional force is. So maybe, I don't know, we might just have to end it here. If we don't, you'll know.